All right, here we go. Today we're going to be in section 4.2. Going to be exponential function, which is where your growth and decay come from. Our first objective will be to graph exponential functions. So in this first example, we will graph and identify the domain and range. Not a big fan of domain and range. All right, so we're just going to keep it simple for now. We'll start off with g of x equals 4 to the power of x. So we know this is an exponential because the x is in the exponent spot. So it makes it exponential. The parent function of an exponential is written as y equals a times b to the power of x. It's generically how they're all made. A is your y-intercept. Nope, I lied. Is it? It is. Okay, I was right. Sorry. I have to think. A is your y-intercept. B is your rate. So basically, if B is less than 1, it will be a decay, meaning it's going down. And if B is greater than 1, it is a growth, meaning it's going up. Correct. So to graph something like this, we don't, so we do. It'd be an imaginary 1. Very good. So that means I'll start at 1, and then knowing this is a growth because 4 is greater than 1, I'm just going to sketch a graph. Technically, this has a little bit more. You could technically add a k here and subtract an h, and then it does all the stuff that we normally do, where the k will go up or down if it's positive, and left and right if it's positive and negative. There you go. So left is positive, and then right would be negative for the h. So for now, there's always going to be a vertical asymptote right there at y equals 0. But if there was a k, then that would move that asymptote up or down. So we go with that so far? All right, let's look at another one. So let's look at k of x equals 1/4 the power of x. How would you graph this? It is. Very good. Somewhat like that. So it needs to be a decay, but we still have this asymptote at y equals 0. Yes, in your point of view, yes. So we'll start up here and then go down and plateau here. Something like that. Okay, so that's what a decay is. So we have a growth from left to right goes up. And then a decay. Well, the y is still at 1. It still crosses at 1. It just is going to be high and then, oh, yes, high to low. Correct. All righty, let's see what else we got. All right, so now we're just going to talk about transformations. Oh, I didn't do the domain and range on those other two. What would be the domain in this situation? It's all real numbers. Perfect. So we write it as negative infinity to infinity. What about the range? Would it be 1 up? Yeah. What's it getting closer to? Okay. Very good. Perfect. What about this one? What's the domain? That's an R. Did I write that right on the other one? Okay, okay, okay. And then what's the range? So if it did that, it'd be coming from the bottom up to here like this. Okay, but you have to do it from least to greatest. It's bigger than 0. So what's the bottom of this graph? 0. And then it goes up to positive infinity. Right? For a domain. But for range, we read it from bottom to top. All right, so on this next part, we'll continue to identify the domain and range. Let's see what else it wants us to do. And then also wants to identify the asymptote, which is kind of what we did in the previous problem already. All right, so 3 tasks, same one as what we just did, just a little bit extra. Given this guy right here, Q of X equals 4x plus 1 plus 2. This is a 4. Very good. So left 1, up 2, good. Very good. And just for grins, what's the y-intercept here? Good. All right, so let's take all that into effects. So this is the way I like to do it. Yeah, so for growth, good, it looks something like this. Good, so what you want to move is that y-intercept. So if the y-intercept was originally at 1, then we want to go left 1 with it, and then what? So I need to go up 2. So my y-intercept is the point I'm moving, goes left 1, up 2, so now it's up to this point. That's not the new y-intercept, that's just the point that used to be the y-intercept. And then to make a growth, where would the asymptote be? Again, we were originally at y equals 0, but we went up 2. So where would it be? If our original, no. If our asymptote originally is at y equals 0, and then we shift up 2, it's going to be where now? 2. The moral of this story, whatever your k is, will be your asymptote. So your asymptote here would be y equals 2. So the equation is y equals k, whatever the k is. And then because you know it's a growth, we just kind of sketch a growth there. Good there? All right, what's the domain? Good, that will probably never change. Okay. Once they get around it. Perfect. That's it. We good there? Awesome. Okay. So we're going to do the same thing, but with something a little different. Objective 2 is to evaluate the exponential function with a base of e. If you recall from pre-cal, e is in numbers like pi. So it's like 2.87 something. So it's just a base, okay? But nothing changes. We're still going to be looking for transformation. We're still going to be looking for the domain and range. And we're still going to be looking for the asymptote. But now it's something that looks like this. G of x equals e to the power of x minus 2. So the only thing changes is that we get an e. And what did I say e was as a decimal? 2 point something something. Is that less than or greater than 1? So it will be what kind of, good, we have a growth going on. Good, so we went right to, it's a growth. Good, and then what's our y-intercept? So when we graph this guy, I originally was here, and then I have to do what with that? Now I'm here. Did my asymptote move? No, and you said it was a what? So it's going to do the same thing as before, but then just kind of shift it. So again, we see that asymptote right there at y equals 0. And then of course, what's the domain? Very good. What is the range? Perfect. Getting any harder? Good deal. All right, that's it for that objective. Let's move on to the next objective. Class seems like it's really flying today. All right, we're going to now use exponential functions to compute compound interest, your favorite. Is that organized? Heck yeah, look at you. It's gonna make it so much easier just that. All right, here we go. These are the type of questions you're gonna have to do. If I give you a word problem that says, suppose that $8,000 is invested at a 3.5% interest for 20 years under the following compounding options. We're going to complete a table. So that's what I'm about to do. So they want you to be able to do it annually, quarterly, monthly, daily, and continuously. Okay. Okay, I'll go ahead and add that there too. Let's skip it. Annually, how many times does that happen a year? So year would be 1. How many times does quarterly happen? 4. Monthly? Daily. Don't account for leap year. Continuously is technically infinitely. It's always doing something. We'll show you what happens there until it gets paid off. Then that's when it stops. Very good point. You're about to find out that daily and continuously is pretty darn close. But continuously will literally do it by the minute. That's how most of your loans go. Where's the formulas? Correct. So your principal goes up and your interest goes down. But you start off by usually paying more interest than you do principal. So they'll get their money first somehow. All right, so there's these two equations. You already know IPERT. You're going to use the equation A equals P parentheses 1 plus R over N raised to the N T. You'll use this one if it's not continuous. Continuous. If it is continuous, you'll use APERT. A equals P times E raised to the RT. So this would be if it is continuous. Okay. You do need to know these two equations going into the test. So APERT and then AP1 plus R over N. All right. No, use the actual E button, which those calculators do have. So A is total amount. P is principal. R is rate. Make sure you put it in decimal form. N is the amounts. It happens in a year. So for instance, annually would be N would be 1. So basically I'll put an N right here. And then quarterly would be 4, monthly 12, daily 365. And then T is time. It was supplied to us right here. It said 20 years. Okay. So that's what we're going to do. We're going to find out how much it is. Okay. So I'm going to run out of room. But this right here, I'm just going to plug in all my information and then we'll try to calculate the answers. So let's see if I can split this up better. So this equation here would be your principal was 8,000. This would be 8,000 times 1 plus what's your rate? How do you convert? Perfect. 0.035 divided by annually would be 1 raised to the 1 times 20 because that's what your T is. And then we would calculate what that is. And then same process, but now you're going to replace all of those N's now with a 4. Very good. Now, what makes this challenging is you don't have them inspires. So you have to be able to do this correctly in a regular 4-function calculator. Now, when it says continuously, now we can use a PERT. So this would be 8,000 E good. All right, now I'm gonna put the answers over here because I ran out of room. All right, so let's play with it. I want you to plug in that first one and see what kind of number you get. And I'm going to do the same, and we're going to make sure you're written the same answer. Then I know you're typing it incorrectly. So here's my recommendation. Do the fraction inside first. So I would do 0.035 divided by 1. Obviously, that's 0.035. Then add the 1, which is 1.035, correct? Then raise that number to the exponent. So 1 times 20 is what? 20. So I'm going to hit the rooftop button and it'll say A and S. So it'll take your previous answer. Rooftop button's right below the pi, but above the x squared. Okay. And then I'm going to put 20 and I'm going to hit enter and what you get. I got 1.98.
Oh.
3.5. Yeah, don't round. 0.035.
Yeah.
Rooftop 20. Good. Okay. Yeah, we're not going to round until the very end because then we'll end up with the wrong answer. All right. So now that we did all that, now multiply that by the principal. So I'll just hit the multiplication button. And you'll see again, it says A and S. I'll hit 8,000 and what you get. Okay. So that's going to be $15,918.31. So always go to 2 decimal places. All right. So try the next one and see if we get the same answer. It's all right. I had to just type it 6 times because I couldn't type the 3. Was your final answer? No. I know, right? You got to add the 1 to that. Okay. And then rooftop. Yes, and then raise it, but it's not 20 anymore. It's 4 times 20. So you would raise it to 80. You can try, but I don't know what 0.000875 raised to the 40th power is or 80th power. You do. More power to you. Nope. Okay, so you didn't know what 4 times 20 is. That's fine.
No. What?
You wrote 4 times 20 rather than 80. So what the calculator just did, it raised it to 4 and then multiplied that result by 20.
I tuned out.
But that's not what you typed. Okay, but if that's the situation, because you might not know what 365 times 20 is, right? But what you'll do is you'll do.
This is a tiny little. I hate the buttons. It's hard to look at.
This is what the accountants do.
This office sucks.
Does it? Okay. So again, we'll do 0.035.
Why is it so far apart? Why are they so large? I keep going. think so. It's 2.
Yeah, because usually it goes 1, 2, 3.
Yeah.
Yeah.
You're not even agreeing. So,
All right, so then we'll take that and we'll raise it to, and now if you don't know what it is, with parentheses, and then do 4 times 20, so that it'll do that first before raising it. So you get 2 point something. Then you multiply that by 8,000. Now you get the right answer. We'll try the next one. So on this one, it should be 16,061.05. Okay. All right, try the next one. See if you get this one. Have all the confidence in the world. I told you the hardest part of this is using a calculator. Yes, that is a 12. Heck yeah, look at you. All right. So 16,093.62. Try the next one. Make sure we got this down. Go,
no,
go through it again.
so stupid.
Oh, you forgot to add 1. It is. So you can see the more times it occurs, the more money you'll end up paying out. So we're now at 6,000 or 16,109.48. Now, what we want to see is the similarity between the daily and the continuously. So now we're going to plug in the APERT version of it. And the way I like to do it is figure out what 0.035 times 20 is. Which is 0.7. And then now I'll go find the E. It is, you see ln above the pi. You see how E of X is in blue. We'll do second, or the second button on top left with the ln, and then we should see E with a rooftop and then a parentheses. So we'll put 0.7 in there. Then take that result and multiply it by 8,000. And what you get? Sure that's not 16,110? Good. Yeah, it gets a little hard there. But now notice that that daily was 16,000. But the daily here was $16,109. And then you'll see that the continuous is 16,110.02. So daily and continuously are pretty darn close to being the same. But continuous goes by that hour or that minute. So it's slightly a little bit more. All right. What else we got? All right. So then any questions on how to do that? All right. Let's look at the last objective then. So tiny. Huh? Well, they thought it was pretty hard to read, so then they just made it even harder. I have no idea. That's what old folks do. So all we're going to be doing is just basically looking at some more application problems. It's all right, I'm sure. Well, he'll go through it too before he gets it. All right, so this is the last problem of this lecture. So I'll write it out and then we'll work it out. So here we go. So in 2006, the murder of Alexander Litvinenko, which is a Russian, makes sense, descendant. This is true. Was thought to be by poisoning from the rare and highly radioactive element polonium polonium 210 to be exact, which can also be written as 210 ho. The half-life of 210 po is 138.4 years if 0.1 milligrams of 210 po is present in a sample, then the equation is A of t equals 0.1 times 1/2 raised to the t over 138.4, which is really the only information you need. Gives the amount. Half-life is any type of radioactivity. How long does it take for the radioactivity substance to be cut in half? So if you start off with 0.1, how long will it take until you have 0.5? In this situation, it takes 138.4 years to have half of the substance you started with. Every radioactive element on the periodic table has a different half-life. Some goes real quick, some takes a really long time. That's why we have to store our radioactive material, because eventually it'll just go to nothing. Well, it won't go to nothing. It'll just keep cut in half into smaller substances. So we have dead sites in the world that we send our radioactive stuff to, and as every 50, 100 years or so, then we can condense it more. The element itself, however it's made, like nuclear plants and stuff like that. Whatever material they use to keep those running, it's waste. And they have to store that waste somewhere else because they can't just throw it on the ground or throw it in the trash. So we have pockets that we just put it underground, contain it, and let it break down over centuries. Yep. But that's what we have to do because there's nothing else we can do with it until someone finds a purpose to use the waste for something else. We've already used energy out of it. That's how we produced it. I don't know. Depends on how much energy it takes to produce some more energy out of it. Is it worth the energy? Which might not be the best thing. All right, what we're going to do is we're going to take that equation and we're going to evaluate the function. This is like math with word problems. All right, now all this fluff that we had to write has a purpose because we have to get an answer and then also interpret the meaning of the answer. And then we're going to simply just round our answers to 3 decimals. All right, so there's your information there. I'm gonna go to a new page because I don't have any room, obviously. Again, the only thing that was really important there was the equation. But you've been waiting for the important stuff. This is what you would write. So A of t, nice. All right, so the first question is, how long would it take, or how much substance will be there if it's 138.4 years? That's literally what it would be. We would literally plug it in and we would get 0.1 raised to the 1/2 of 138.4 divided by 138.4. That's just 1, which ends up just being a half, and half of 0.1 is 0.05 milligrams. That's it. Super easy. We didn't even need a calculator. Let's do a harder one. How much would be left after 276.8 years? Basically double that. Yes. So that would be 2. So what's 1/2 times 2? What's 1/2? Sorry, 1/2 raised to the 1/2 raised to the 2 power. So this is to the 2nd power. Yes. All right. And then what is a 4th of 0.1? There's a 2 in it. Basically, what that ends up being is half of a half. So what's half of 0.05? But where would the decimals go? Very good. So that's how much would be left. Or you could just type in the calculator and get the same answer. Right? Last one. What would be left after 500 years? Something's not nice and easy to use. This one we would definitely have to use a calculator. See if me and you get the same answer. Point 72 would be more than what you started with. All right, so start off with what is what's 1/2 as a decimal?
1/2 as a 0.5.
Okay, let's start with 0.5.
Why?
It's an X
God,
value
I
actually.
that.
All right, and then rooftop, parentheses. Go ahead now and put 500 divided by 138.4 in it. Oh, you can write that number down if you want, yeah. And then hit enter. Now take that result and multiply it by 0.1. There you go. Now, if you wanted to do this first, you could, and you would write that decimal down and then 1/2 raised to that number. Oh. Okay. Now what'd you do with that? Ah, you can't multiply by 0.1 yet. You'd have to. Well, no, you did this. Oh, that's not multiplication. That result is being raised and you're multiplying it. I see now what you're doing. So in this case, it would literally be 0.008 milligrams. And that's it. Just literally the entire lesson in one day.